Good afternoon, everyone. I'm Abhay from EDS Technologies, and I will be your host for today's webinar. First and foremost, on behalf of EDS Technologies, we thank each and every one of you for taking your time out and joining this webinar. So, we have titled this webinar as Enhance Structural Performance and Efficiency of Composites with SIMULIA Abaqus. So before handing it over to Dr. Danish and his technical presentation, I would like to begin this webinar by giving a brief introduction about our company, EDS Technologies. EDS Technologies Private Limited was incorporated in 1994 to focus on providing PLM solutions, implementation, and support. We are the largest technology solutions provider in India and also the platinum partner to Dassault Systems. We have served more than 2,000 customers across India, and we operate in 9 locations with our headquarters being at Bangalore. We also have various strategic partnerships with world leaders like EOS for additive manufacturing requirements, Human Solutions for ergonomic solutions for automotive and aerospace industries, Technia for ensuring product data quality. For military simulation and training needs of aerospace and defense industry, we have partnered with MAC for visual simulation solutions. We also have strategic partnership with Esri for GIS requirements and with Synopsys for EDA solutions. We have a dedicated sales, support, marketing, and customer satisfaction teams to address customers' PLM business and support requirements. In today's webinar, we are joined by Dr. Danish Handa. Dr. Danish Handa has completed his PhD from IIST Trivandrum, specializing in machining and manufacturing of composites. He has nearly 2 years of industrial experience in the manufacturing of composites. He also works extensively on simulation of composites for the past 6 years. Currently, he is working at EDS Technologies as a solution consultant for SIMULIA brand. Over to you, Dr. Danish.
Thank you, Abhay. Good afternoon to all, and thank you for attending this webinar. The agenda for the webinar is we will be introducing about the solution, what is known as SIMULIA, and what as a package it does. Then we will start with the basics of composite simulations, and then we have some case studies based on the real life applications, and we are planning to conduct a separate webinar for the future works and further what all are the availabilities in the solution, and then some of the customer references and Q&A round. So moving forward towards the SIMULIA's power of the portfolio, like as a SIMULIA package, we not only offer Abaqus. Generally in the mind is like, okay, Abaqus is an FEA software and it does all the work. But in the SIMULIA portfolio, what we are having is 4 things, that is Abaqus, iSight, EFISAFE, and Tosca. Abaqus is an FEA software which usually models and do the FEA simulation. Then we have iSight, where we do the complete optimization based on the geometry as well as the manufacturability. Then we have EFISAFE, sorry, yeah. So what it does is it's basically works on the fatigue and durability analysis, where the crack is present and how the fatigue analysis can be done. It all can be done in your EFISAFE. Then we have the Tosca, in which the non-parametric optimization can be done, such as for your optimal design, your structure, your fluid flow. So this was the brief introduction about the SIMULIA and what the portfolio does. Moving towards today's agenda, like overview of composite simulations, we will be moving few case studies. We will be taking few case studies in this, where we will be covering around 9 case studies where simulations such as honeycomb structures, impact testing, and real-life applications such as windmill, drones will be taken care. So starting with the basics of composite simulations. So basic, what we know is composites nothing but a combination of 2 materials with having different properties. For example, in this particular case, we are taking glass as a composite, glass epoxy as a composite, plus we are adding aluminium too. So this is just a basic understanding how we provide the layup to the particular component. So you can see at the screen, that we have given a particular, there is a particular plate, and we are providing material properties as well as thickness based on the prepregs or the particular resin systems with respect to your glass or carbon fibers. So in the module, what we can do is, after applying this particular uh, layups, we can actually visualize it. For example, I have selected this particular side of the plate, and here you can see that with respect to the thickness, we have got the orientation of the plies, ply 1, ply 2, ply 3, and based on the orientation what we have given in the previous slide. Similarly, the center slide, we have made it thicker in nature. So when we selecting the particular side of a plate, we can see the orientations are clearly visible with respect to the reference what we have taken. Then, like all FEA softwares, we give the boundary conditions and the loading conditions, and such kind of results can be adapted. Here you can see the one maxi stress for a complete element, but in the software we can also visualize the ply by ply stresses. For example, I only want to visualize the ply 1 stresses. So here you can see ply 1 is visible, as well as the amount of stresses that are generated in ply 1. When we move towards the ply 5, here you can see that ply 5 is only for a particular center component. So the stresses are changed, and these are the ply 5 stresses what has been generated. So it not only works for the entire component, but we can actually visualize the ply by ply properties. Now moving towards the global case studies, as this was an introduction like how basically we work on composites in the FEA solution in Abaqus. So first of all, moving towards the XFEM tensile testing. This is a basic study which everyone does when we have to manufacture any kind of composite. So this XFEM is nothing but the extended finite element method which we are using for creating a crack, and then we have to visualize that how this crack has been propagated. This can be used for any kind of geometry, for orphan meshes from other softwares, as well as the combination of two. And we can also have an arbitrary crack or a stationary crack to visualize. So here you can see these all are the properties. We have made a dog bone shape specimen according to the ASTM standards, and the damage properties as well as the elastic properties based on the engineering constant. We can use lamina properties, orthotropic, any kind of properties we can use, and we can model our test specimen. So this is an overview how we basically do it. So here you can see we are selecting a particular composite as a element, and after that we will be providing our material sectioning. And doing the material sectioning means we have already made it as a composite, and now we are giving the assigned material orientation. So based on the selection of a particular component, we will be providing a particular orientation with respect to the coordinate system. That can be local coordinate or a global coordinate. So we can actually make our own datum systems and provide a particular angle, and you can see here the angle orientation has been made. So this is how the orientation can be given. This is one method of doing that. Second method I showed in the previous step how we do. Now this a crack has to be generated. So we are using an XFEM method to model the crack inside the component. Based on that, we are picking the component, we are picking the region of the crack, and then we are inbuilting the crack. Sorry. Yeah, so this will basically make your particular specimen, and we are providing the loading condition as a tensile loading, and this you can see the results how it will work. So this is how the crack will propagate and your tensile test is happening. And we can have the post processing as well. You can get the stress strain curves out of this particular thing and whatever outputs we require. Now moving towards our second case study, that is our VCCT technique. That is nothing but the virtual crack closure technique. So once we need to understand what is mode 1 crack growth for a double cantilever beam, this is an example. So, and moreover, the applications can be used where two bonded materials are there. You need to understand the delamination or the debonding of composites, adhesive failure of the composites. So all things can be covered in this particular case study. So here you can see we are actually making a beam element, and then while doing the assembly, we are selecting two beams simultaneously to bond each other, and then this bond we are making in between. We are having a particular cohesive bonding inside this while giving the interaction. You can see here the cohesive bonding has been made. So giving the interaction properties, after that what we will do is we will go for the interaction manager and we will give all the behaviors. For example, your fracture criterion, your normal behavior, your tangential behavior, how much friction it is acting. And similarly, as I told in the previous slide, we are giving the crack. Here we are using debond using virtual crack closure technique rather than XFEM, and giving the particular contact pair. And this is how we are basically making a specimen out of virtual crack closure technique. And if you see the results, you can see how the debonding has been taken place when the adhesive is there and two materials are bonded towards each other. So this will be helpful for most of the studies where your delamination, debonding, or adhesive bonding has been concerned. Then moving towards your case study 3, this is the impact load. So in this example, what we have performed is like a ball is there and it is getting a velocity over a particular plate of composites. This is very much useful where your ballistic kind of applications are concerned, where you are using a Kevlar fiber and a bullet has been shoot and how it will behave. In this particular thing, we will learn how we are giving a particular property. This is basically a assembly, and when we are giving the property, what we have done is here we have make a particular specimen and partition it. Partitioning it, making a single layup. This is another method of providing a layup to a composites. So we are creating different layups. You can see here approximately 7 to 8 layups has been created. And then what we are doing here is we are providing the loading condition. So here the load has been given to a ball with a velocity. And how it will behave now is, you can see here the ball has been giving the impact load and it is getting dispersed into the panel. And you can see, if you zoom, you can see here the layers are getting displaced. So layer by layer, if you want to understand how we can see how much a particular layer is getting, for example, layer 2 is there, and we want to visualize only what is happening in layer 2. So we can select that layer and we can see how the stresses are getting generated because of this impact and how what are kind of stresses are acting. We can select any output, stress, strain, displacements, and if we want to understand the criteria, failure criteria such as SIVU, SIHIL, all are possible. Yeah, so moving towards our case study 4, that is the wing simulation. Now we are coming towards the more application based side, and this geometry was a courtesy for the Boeing company. Yeah, so here we will learn about the layered continuum elements, like how the layering has to be done over for a composite material with respect to your aluminum. So what happens is, it's a green color, if you can see, it's an isotropic material, and the beige color you can see it is basically a composite material. So it's a combination of aluminum as well as your fibrous composite. So this is how the assembly is, and we are providing properties for different case. Here we have selected different criteria for all the given layer ups, and we are giving a particular boundary condition where one end is fixed and one end has having a particular load. So it's kind of a pull load. So you can see here again such a kind of simulation for a wing is generated. Similarly, in this case as well, we can see the property in such a manner that we have the layup by layup understanding of how much stresses has been generated. And then we are moving towards a case study which is having a yacht hull. This is actually an interesting case study because here not only the layer by layer, but we are producing some kind of patches, because some staggering on some kind of ply drop analysis when we do in a particular composite material. So how we can understand what is happening in a particular area. So this kind of simulations are very helpful in that sense. So this is a particular yacht and we have made almost 108 ply count on a particular surfaces. You see, we are actually selecting different surfaces. We have put patches, we have put cores in it, and different properties of different glass fibers or core properties as well as thicknesses has been given. And then all the loads, including your hydrostatic, your inertial loads, whatever we are inculcating in water, has been inputted in this, and the simulation has been run here. So this is a kind of simulation or loading condition that has been used. Again, when we see the results, we can go with a ply by ply result orientation. For example, many plies are there. So when we select one kind of ply here, suppose hull top is there. When we apply, you can see only the top of the hull is showing the analysis results. That too for a ply number 3. So similarly, for this condition, we can have the results for ply 1, ply 2, etc. Then similarly, we are going for different stages where different areas of hull has been selected, and we are actually applying a load here. Sorry, the analysis results here. You can see the inside how it will behave, the outside area how it will behave. So certainly these kind of analysis, it will be very helpful when patches has been generated. Suppose somewhere the thickness of the material is high, somewhere the thickness of the material is low, a number of plies are more. So for every ply we can see how it is behaving. Yeah, so another interesting thing in the particular portfolio is the honeycomb structure. Nowadays, the applications has increased a lot. For example, in telescope mirror structures, your rocket substructures in aerospace industry, then your snowboards in sports industry, automobile structures, loudspeaker technology in audio industry. These kind of structures are made, whether it's an aluminium honeycomb structure or a foam honeycomb structure or carbon itself honeycomb structure. So many kinds of structures are available. Normally in the module, we have to make this structure while doing the modeling in some of the software such as CATIA or SolidWorks. But in the particular module in Abaqus itself, we are having a plugin where we can basically have, suppose these two parts we have created. We have a plugin known as Create Honeycomb, and here we can select our lengths and cell sizes, cell width, length, everything, and your honeycomb structure is ready. So we need not to make anything extra while doing the modeling and then make it. So here we are generating a particular structure which is having two face sheets of 1 mm each with 4 ply thickness of 0.25 and giving the damage properties such as Hashin damage criteria or maximum damage criteria for this particular structure. Here you can see when the region is picked, your layups are there, and for a 0.25 means it's almost a 1 mm thickness of a particular face sheet. Then assembly wise it will look like this as a honeycomb structure, and then we are giving the loading condition. So we have done 3 case studies in this particular case study. That is, we are giving uh, a bond as a strong bond in one case. Second case, our bonding is weaker and we are having a tensile load for both the cases. And third case is your pressure load that is acting in a compressive way. So how the results will behave. Here you can see this is the case where your strength is very high of the adhesive with the face sheet. You can see the aluminium actually is getting displaced, or you can get distorted, and this is one case. Then when we move towards the second case, you can see it's a compressive load basically, and aluminium actually is getting disoriented and the face sheet is going down. And the third case interesting where basically we do that, nothing is happening to our aluminium structure, but the weaker bond, due to the weaker bond strength, the face sheet is moving up. This is a thing when we do for peel testing and all this kind of testing. Yeah, so now we are moving towards the orientations where we are using real life applications such as windmill structure is there. So in the windmill structure, what we are basically doing is we are creating different parts in software such as SolidWorks or CATIA, and we are giving the orientations as well as whatever parts are there in the composites, and aluminium or some other material we are using for other parts. Here we have considered wings as our fully composite material, and this is how your assembly will look. What we are giving here is the loading as a wheel will rotate, and the other things are fixed in nature. To understand that how the wings will behave, what kind of loads will be there. Similarly, we can perform for the air. Suppose air is acting in a different way, or a cyclone has come, how much load the air can put on the wings or on the uh, structure itself. Such kind of analysis can be performed here. And then you can see the results of the case study. The wing is actually moving in a particular way, and these kind of stresses are acting, and the colors will change, the contours plots will be happening, and we can get the different results for the particular case. So this is one of the case which we have performed for the windmill. Secondly, we can perform where the pole can get break. We can give the uh, uh, damage properties of aluminium using Johnson Cook model, or damage properties of wings using Hashin damage criteria. We can get the psi heel, psi wu properties, how much is there, to understand whether the structure is failing or not, and von Mises for your metallic parts. Yeah, so moving towards the drone simulation, here also several parts are there, and we are creating our geometry in the SolidWorks or CATIA, and then yeah, so then we are giving the properties similar to the layup sections and everything, and yeah, once the region is picked, then we can see that the layup orientation has been generated here. What our main motto was, suppose the load is very high on the wing section and your drone is very rigid in nature. So how the wings will behave, whether the breakages will happen or distortions will happen. Normally, the failure of your composites is brittle in nature. So we do expect that the wings, if it is breaking, what will be the nature of the breakage of these particular wings? So this is what we have modeled. You can see here the breakage of your wings when the load is very high in nature and the part is very rigid. So this is one of a kind simulation which we have performed. Yeah, so here we have taken one case study of airplane where we have used a particular Hashin damage criteria as our breakage criteria, and we are using a concrete block where the airplane will crash. For we have done the simulation for both aluminium as well as the composite, the entire plane as a composite and entire plane as an aluminium, and this is the assembly. And yeah, this is the loading condition what is been, but it's like at a particular velocity the airplane will be getting interacted with your, or getting collided with your structure, the concrete structure. So the concrete structure, we have kept it as a rigid part, and the airplane will be basically deforming. So here we will see what is the difference between the deformation, or what is the difference between when the airplane crashes or any kind of rupturing is happening between the composite as well as your metallic part. So for example, this is first case for the composite. Here you can see it's more of a brittle failure that is happening. There is hardly any deformation that is taking place. Basically a plane is getting crushed over here, and we will not have much of a high-end deformation in any of the component here, because entire part is made up of CFRP. Yeah, so you can see here, this is basically how the crushing of your CFRPs or your fiber reinforced composites happens. Yeah, so moving towards your aluminium case, where the deformations will be very high. You can see here the deformations, even the wing will deform, or the entire plane will deform once it is getting contact with the wall. So high amount of entire plane is getting deformed, including the wings of the aircraft. So this is the basic difference when it comes towards the analysis of your metals as well as the composites, fibrous composites. So this was the entire agenda of a particular presentation, that we need to showcase what the capabilities of the software what we are having and what all analysis it can do at a basic level. Now we are moving towards further webinars what we are going to conduct on composites, and this will be based on the random fibers. Suppose now in this particular uh, webinar I have shown you about the generation of fiber reinforced properties where it is a unidirectional fiber. So in later cases, if we are inculcating any random fibers 2D or 3D into a component, so that is possible. Then if we want to have a particular modeling where we have to do a micro scale analysis, where a single fiber is embedded into the matrix or a series of fiber is embedded into the matrix, and we don't have the three-dimensional property for the same. So using the Mori-Tanaka equations that is inbuilt in the RVE module, we can basically get these particular equations. Even you have the 2D properties of your matrix as well as the fibers. Then we can have your three-dimensional properties for like EXX and your elasticity, shear modulus, as well as your Poisson's ratio. And then we can perform the analysis. So yeah, so as I was telling, that we can do the parametric studies also, where your fibers, single fibers are embedded into the matrix, and characterization can be done in the micro scale. Then how this unit cell of your textile, that is your bidirectional fiber, will different weaving condition, such as satin weave, plain weave, etc., can be characterized, and we can actually do these studies. Then definitely how these particular things can be incorporated into your main component, what you are making. So these all things are possible in the software using some of the plugins. Then we have another add-on plugin known as C-Zone, where suppose a Formula One car is there as an example, and it is actually in interaction with the rigid pole, that is uh, how this will behave, whether it is only deforming or crushing is happening. So the C-Zone basically plugin is there, where we have the crushing analysis of the composites and how it will behave. So this is also a very important particular plugin, where we can actually go through a scenario where lot of even I showed the aircraft model, and similarly your bike can get into a particular pole, or it can basically how it is sliding, what can be done, whether some kind of breakages are there. So this C-Zone plugin is very well structured in such a way that very perfectly oriented crushing will happen, uh, because once we do in any kind of software this crushing analysis, sometimes our meshing is not that up to the mark, and it will show us the error of deformed elements, and then we have to go for a very high number of like very fine meshing. So these kind of things can be avoided, and we can get a very good crushing analysis results. And one more very nice thing has come is like WCM plugin, that is wound composite modeler. As of we know that the era is moving towards hydrogen tank, and where liquid propulsion rocket engines are concerned, we need some cryogenic kind of tanks which can withstand a very higher pressure, such as 500 to 600 bars, and then type 5 type 4 cylinders of hydrogen and helium that has to withstand 60 bars of pressure. So this basically plugins allow you to understand how the liner or linerless tanks can behave in a particular manner, where you can have orientation in such a way that you can provide your hoop and helix winding orientation and the properties of the liner itself in the module. So if you can see here in the left hand side of the screen, your liner properties has been given here. What is the Bose radius, what is the base wind angle, everything is given here, and how this particular thing works with how many layers of fibers in what direction. So this is with respect to the filament winding process, which we use for understanding the model of your cylinder, basically. Yeah, so moving towards your next thing is, as I was telling, you can actually put your helix and helical and hoop layers both. You can see here in the left hand side, the material is T1000, that is Torre grade your carbon fiber, and how much thickness it has to be winded on, how much wind angle is required, and how the layer has to be winded onto the cylinder. Such kind of studies can be done. Similarly, in the right hand side for image, you can see that the hoop direction has been given, and a particular rubber has been uh, transported into the layers between your liner and your this thing. That is to avoid any kind of uh, permeation in the, particularly for the permeability, where the leakage should be avoided. So such kind of studies are also happening in a software, and we can get good results in form of your uh, stresses, how much basically pressure this particular tank can withstand. There are a lot of case studies for this as well. So these kind of basically structures, and for example, in this particular case, we are having a maximum stress here. This is in terms of Pascal. So whether our tanks can withstand any kind of buckling, any kind of internal pressures uh, due to the sub-zero temperatures or due to the gaseous temperatures, whatever pressures are generated, how much we can compress this gas. So this is very helpful where your rocket studies or your nowadays even your LPG cylinders are made up of glass fiber materials. Similarly, your hydrogen tank, as government is proposing hydrogen fuel, how these hydrogen tanks can be made, which can withstand up to 50 to 60 degree, 50 to 60 megapascals of pressure. So such kind of studies are very useful, where you can decide how much thick layer of a particular fiber you have to install, and so that you can save the weight, save the your cost of a particular tank. Yeah, so for the reference, customer reference, if I could say, then we have quite a good amount of customers and very renowned customers who are there with us for the this particular composites, including DRDO, CSIR, VIT Wheeler, even Indian Institute of Science, RAFE, SABIC, DUMS, it's a drone company, then BASF, Axis, Cadis. So all these companies are with us for this particular thing, and we do connect with the customers in a way that we are supporting, as well as we are promoting their projects. We are supporting in the ongoing funding projects also what they are getting, and we are delivering them very well in this particular manner. So all agenda of this particular presentation was to make you basically understand about how this particular solution works and what are the capabilities of the solutions. And this also includes the thing known as subroutines. So subroutines is nothing but the coding which we do for getting the outputs. For example, some of the models are not feasible in a standalone case, where your any kind of simulation whether any kind of FEA software is unable to do. We can do the coding in Python or Fortran, and we can get the output into your Abaqus. It's very well linked with Python as well as Fortran. We can get the element based models. We can get the as I was showing you about the fibers that has to be randomly inbuilt into your matrix. So these kind of things, we have prepared some plugins for our customers, where we are delivering them such a thing, and even we are supporting with their such products. Even this will help in civil structures as well. Yeah, so that's it from my side. Thank you so much for listening.
I would like to thank you, Dr. Danish,
Thank you.
for delivering such a informative webinar. I'm pretty confident that it was helpful to our audience as well. I would like to also thank the audience for taking their time out and joining us for this session. In case if you have any further queries related to the subject matter or any other simulation requirements, you can always connect with us. Our details are displayed on the screen right now. You can reach out to us anytime and we'll be happy to address your queries. So please do keep an eye out for our upcoming seminars and webinars. You can follow us on our social media for the same. So see you at the next session. Thank you.